And I've got here two things which look a little bit similar, but which aren't, obviously. Spot the difference, gives the game away. And so the first one is, I've got some angle, x, I square it and find the sine of that angle, sine of x squared. And here, this is another way of writing, if you remember, this, where I've got a missing angle, I find its sine, and then I square that. So the difference is when the squaring happens. And that affects how I differentiate it. So firstly, a reminder about what happens when you differentiate sine. Sine becomes cos, cos becomes minus sine becomes minus cos, and minus cos becomes sine. You get that lovely little circle. So this one I differentiate just using the chain rule. So the sine of x becomes the cos of x. So the sine of x squared becomes the cos of x squared, multiplied by what you get when you differentiate the bracket, which in this case is 2x. Sorry, we're not doing plastic dinosaurs. That's so I'm not going to write that as 2x cos of x squared. And to be honest, I only really put the brackets in to try and emphasise the difference. Probably wouldn't get that. So that's how you differentiate the sine of x squared. How do I differentiate the sine of x squared? Well, remember, this is how it will be presented to us, but this is what it actually means. This notation, and I have no idea about the origin of it, but this notation is a short way of writing that. So I differentiate that as I do something like that. Multiply by the power, reduce the power by 1. So I multiply by the power, reduce the power by 1, so it becomes 1. But then, of course, with any bracket, I then have to multiply by what I get when I differentiate the bracket. So I get, and for those of you who are ready and raring to go for tomorrow, that will ring a bell. You could rewrite that as sine of 2x. So those two things are very similar in the way they look, but the way we differentiate them is different. We differentiate this one using trig differentiation, we differentiate this one using the brackets method. Of course, I could differentiate this using the product rule. Sine x squared is sine x times sine x. So I could differentiate it using the windows. And I'd get the same answer. So there we go. So that's a key thing. I perhaps should have done that when we did trig integration, but sorry, I keep doing it. Trig differentiation. Integration is after half term. But there we go, I've done it now. While we're talking about half term, you may well be aware that we have this sort of semi-mock period coming up around each side of half term, and we have 2 maths tests scheduled, and I don't want you to get overwrought by the importance of those. I'm just going to use that to do 2 progress tests of the sort that we're doing tomorrow. So the first paper we do, which will be just before half term, will be on all this differentiation stuff we're doing, and I'll make sure before too long you've got a nice list, clear list, so you know what it is. I mean, I'm going to be slightly less helpful about what exactly is going to come up, but I'll give you a list of all the things we covered in differentiation. And then the one we do after half term will be a stats and mechanics one. So it will include the stuff we did before Christmas on regression and correlation. It will include the stuff we did earlier last term on moments. And I'm hoping that we get some mechanics done this half term as well. Differentiation is going well. If the progress continues and we all stay healthy, then hopefully we can do some mechanics this half term as well. I am going to start, I think, doing some mechanics in videos. It's just a bit of an insurance policy really, so I think I'm going to cover some chunks of the mechanics syllabus by producing videos, which I hope you'll find time to watch, in your own time. I mean, if we have time at the end of the, around Easter to go through those things in class, that's all very well. But I just want to make sure that, I do right by you, that we cover the full syllabus and we have enough time to revise properly. So, anyway, I'll worry about that closer to half term. So, let's move on today. And today we're going to carry on differentiating, and we're going to add another string to the bow of the things that we can differentiate. So today we're going to approach differentiating things that look like this. And you could probably have predicted this where we were going next, because we've so far looked at differentiating single things, so single brackets to the power of something, single terms involving e, single terms involving log, single terms involving trig. We can differentiate those single terms being added or subtracted by just doing each of them individually. And then last couple of lessons we've looked at differentiating products, where you've got one thing multiplied by another thing. And it's not perhaps surprising that therefore we now are going to look at differentiating one thing divided by another thing. And this rule that we're looking at today has a name which we've come across before. When you divide one thing by another, the answer is called the quotient. You have the quotient and the remainder. So this is the quotient rule. And the great news about the quotient rule is that it is on the formula sheet. So, let's all whip out our formula sheets. Oh, hold on. Well, actually, I don't know.
I can get it on here.
Well, let's just see. You got yours? There we go, right. It looks like we're going to be okay. That's good. Right. So, except I haven't got one now. So, if I find it in my OneNote version. So it's at the bottom of the page 6, which is the page we're going to be using later this lesson to fill out our I Love Trig sheet. And it's in a table of things that oh, for goodness sake, sorry. It's in a table of things that we can differentiate. So we are told here that the tan of x becomes sec squared of x, and we're also told how to differentiate sec, cot and cosec, although actually we're going to use the quotient rule to do that. But here's the quotient rule. If we've got a function which can be written as one thing over another thing, this is what dy by dx is. And it looks horrible. It's very, very simple and very, very similar to what we were doing with the product rule. Hello.
Hello, sir.
Who are you going to
COVID
take?
queue is very, very, very short. If anybody would like to go down there and get it done now. Anybody that's signed up for it.
Wait, did I have to fill in something?
I think you signed up for it, didn't you?
I just emailed you.
Yeah, no, that's fine.
Take her anyway.
Thank you. So if you make your way over there and just join us.
Well done, Beth. Right. Yes, so I forgot what my question was. Sin x over e to x. Right, so I'm going to write it again over here so we can keep that on the board. So what we do is we set up our windows just like we did for the product rule. This time, though, it's important that the numerator goes here and the denominator goes there. With the product rule, it didn't really matter which way round we did them. And I think we always did it that way, but there we And I'm going to differentiate. So sine becomes cos, e to the x becomes e to the x. So using the notation they're using, this is my f of x, and this is my g of x. That's my f of x, that's my g of x. So this is f dash of x, and this is g dash of x. So what do we do? What does the rule tell us we do to find dy by dx? F dash of x times g dash of x. Well, that rings a bell. That's what we were doing with the product rule, weren't we? So, I don't know which way around do I want to write that. I'm going to write it like this. Doesn't really matter. Ah, here's a difference to take away. It was a plus with the product rule, wasn't it? What am I taking away? F of x times by g dash. Oh, right. So it's the same as it was with the product rule. It's just a minus between the two. And the big difference is that with the quotient rule, everything then gets divided by this squared. And I'm hoping you can see that e to the power of x times e to the power of x, multiplying powers are the same thing, you add the powers. So actually, that's e to the 2x. And as is often the case with the product rule, there's scope for a bit of factorising up the top there. I mean, it depends on the context of the question, but that's it. That's all. That's the sort of thing we do. Now, again, the justification for that is not something we need to worry about, but it's on the formula sheet. And of course, although the product rule isn't on the formula sheet, it's the numerator with a plus rather than a minus. So there's that reminder there, although I think most of you will just get used to doing the windows, and that's all good. So here's a very similar question. Our function is almost identical, slightly different. And we're asked to find the turning point, the stationary point. So we're going to find dy by dx, and we're going to ask when does it equal 0. Now you might be thinking, oh, that looks really complicated because you've got the whole fraction thing. But just remember, 0 is your friend. Have a go. So see if you can go through that process again. It's very similar to the one we've just done, just with that subtle difference. Remember, when you differentiate e to the 2x, you get e to the 2x multiplied by 2 to e to the 2x.
Yeah, I think we're not planning on doing lots of things. So I think I didn't take it pretty so I'll make sure that 21. So yeah. Will you be alright? Thank you, Matt.
That's it. Yeah, how much is that?
Right.
So we're looking for the turning point, stationary point, so we ask when does it equal 0?
Before half term, if you can let me know whether you want to half
Thank you very much. That's wonderful. Thank you very much. Bye.
So I get to here and I ask when does it equal 0? I don't know if you saw that we can write the denominator as e to the 4x, e to the 2x squared. And that's great news because the first thing I can do is multiply by e to the 4x, which means that the denominator disappears completely because 0 times e to the 4x is e to the 4x. At the same time, I'm going to factorise the top. I need to put the 2 there, don't I? Because I can pull out the e to the 2x, leaving me with that. So straight away, something that looks horrible, if we're asking when does it equal 0, becomes really easy. We can multiply both sides by the denominator, and because 0 is your friend, it stays as 0. And the good news continues because we know that e to the 2x is never 0. There's no value of x that will make e to the 2x 0. So we've got no solution there. So my only solution is this. When does that bracket equal 0? And we did one like this yesterday. This is one that's going to give us a tan. So hopefully you were able to spot that. Where you've got a cos and a sine, that's going to give you tan. So you get that. I'm going to divide by cos x because I can if I end up with a tan. Oh, that rhymes. Never knew that. I can if I end up with a tan. Right, so I get 2 sine x over cos x, so that's 2 tan x. So basically tan x is a half. And it's even just x, isn't it? It's not 2x or 3x. Oh, well, easy peasy then. So, yeah, there we go. So I've got, I'll do shift tan of a half and just being lazy. So you get a not very nice value, which you could then substitute in to get your full coordinate. So this is the great news about the quotient rule. Answers are always going to be fractions because you're always dividing by v squared. But if it's a turning point question, happy days. Happy days. No denominator to be troubled by. Right. I'm keeping an eye on the time. So can I just get you to try, no, sorry, I want the equation of tangent. Here we go at that one. Now that's, sorry, so that's 1/3 of x, e to the power of a third of x. This is on page 245, if you've got a book, but yeah. No, sorry. So this is a tangent to the curve. It's e to the 1/3 of x. over x. So tangent, so you're looking for a point, we've given that. Looking for a gradient, I get that by making x equals 3 into this. Leave it in terms of e though, please don't sort of go with decimals. Ooh. Yeah, it's interesting, isn't it? You get a gradient of 0. Did you get a gradient of 0 in your... There you go. Yes, you get a gradient of 0. Because when x is 3, a third of x is 1, so you get e to the power of 1, but that becomes 0. So the gradient is 0. So what do lines that have a gradient of 0 look like? Well, they look like this. They're y equals lines. So for example, you know, if it goes through 1, then it's the y equals 1 line. So we know that this line is going to be equal to y equals no x's plus something. We're going to substitute in that value. So we have to make x equal to 3. Well, that's irrelevant, becomes nothing, and y equal to a third of e. So you get that. So the equation of the line is y equals a third of e, which is a horizontal line. Now the quotient rule is really useful for things that perhaps don't look at first glance like quotients. For example, now we already know what we get when we differentiate this, so this would be an opportunity to throw in the proof of that. I can write tan x as a quotient. So go on, see what you get when you do that. We're hoping we're going to get sec squared x. And maybe some of you might get on to doing cosec x. Think about how you can write cosec as a quotient. Remembering what cosec actually is. Two cosec? I don't normally, I only normally have the little window open up, but Norman quite there.
Alright, take it, focus.
It's quite neat, isn't it? You end up with cos squared x. It's minus this, but that's minus sine squared x. So we actually end up with plus sine squared x divided by that squared, which is cos squared x. And I know that cos squared plus sine squared is 1. And the other way of saying 1 over cos squared is sec squared x, which is the thing I told you the other day. Now, that's not a super good proof because it involves the fact that sine becomes cos and cos becomes minus sine, which we haven't proved. But you know, that's pretty good. Can anyone suggest how I could write cosec as a quotient? I can write it as 1 over sine. Cosec is 1 over sine. Remember the third letter of sec, cosec and cot tell you which one it's 1 over. And so that's a quotient. And the great news about when you've got a quotient like that is that when you differentiate 1, it disappears. What that strictly means is it becomes 0. Sin x becomes cos x. So I end up with 0 times sin x, nothing, minus that times that, now if I go back to the formula book, I'm fairly sure that sec is there. And it's written it as, oh no, sorry, cosec. It's written it as cosec x. There's no k, so we don't have to worry about that. So it's cosec minus cosec x cot x. So Is that what we've got here? Well, let's write the sine squared as sine. That's what sine squared actually means. And then, yeah, I can split that up as which is minus, well, that's tan is sine of a cos, so that's cos of a sine, so that's minus cot x multiplied by 1 over sine, which is cosec x, which is what we're told. So, you know, I mean, we don't need to remember that, but that's just the point that you can use the quotient rule with things that don't immediately look like quotients, which is quite a neat trick. Just do sec for me. Just differentiate sec. Y equals sec x. We know what the answer is going to be, but let's just see if we can get it using the quotient rule. So I've done cosec, which was 1 over sine. Sec is 1 over cos. Yeah, other way around. So it's quite good to do this just before a trig assessment. Don't forget, you know, this sort of stuff is part of what we need to be able to do. So it's not all double angle stuff, and you know, those sorts of things are worth doing.